and volume. Throughout this video, I'm going to be doing lots of calculations. Don't worry about the numbers, just think conceptually. Let's start with just a square. Say you have a square that is 5 centimeters by 5 centimeters. The area is simply the base times the height, which is 25 centimeters squared. And what this means is that there are 25 1 by 1 centimeter squares inside this square, just like this. The same will work with a rectangle, base times height. So this is just 50 centimeters squared. Now for triangles. Let's do one with the same dimensions. Now a right triangle looks just like half of a square, so it makes sense that the area would just be half of the base times the height. Now an equilateral triangle is a little different, but as you can see, it's still half of a square. So 1/2 base times height. Trapezoids. These look a little different, but the same concept applies. Base times height. But because there are two bases, let's just average them, and then multiply by the height. Parallelograms are not any different either. Base times height. This works because if you take off this right triangle here, you can just put it on the other side, and now it's just a rectangle. So just base times height. Now circles are also just base times height. You may think I'm crazy, but it's true. Divide this circle into an endless amount of equal pieces. Now I can't physically do that, but for now 16 pieces will do. Now rearrange your pieces of pie like this. Point down, point up, point down, point up, until you have all the pieces together. Now when we're done, this is going to look pretty close to a rectangle. If we actually divided it in an infinite amount of times, it would be a perfect rectangle. So now what's the base and what's the height? Well, this right here is the radius, so that means that this side right here is just going to be the radius. Before I get to the other side, let's talk about pi. Everybody knows that pi is 3.14159. But what does it mean? What it means is if you go all the way across the circle instead of all the way around the circle, it's approximately 3.14159 times longer to go all the way around. So as you can see, we put half of the circumference on each side of this rectangle here. So if you divide it by 2, it's just pi r. So that side is pi r. So now base times height is pi r squared. Now it's time to go over volume. All we do when we take the volume is multiply the area by the dimension that we added when we went from area to volume. So in this case, it's going to be 25 times 5, which ends up being 125 centimeters cubed. This means that inside the cube there are 125 1 by 1 by 1 centimeter cubes, which are these little things right here. And it will work the same way for a rectangular prism. Cylinders are easy. It's the area of the base, which in this case is pi r squared, times how far it goes out, which we could call the height if it were standing up. Now for pyramids. Area of the base times height, right? Yes, except for one problem when it comes to pyramids. If we just did the area of the base times the height, that would give us the volume of a rectangular prism. So let's just divide it by 3, because it comes to a point. When everything comes to a point, we'll divide the area of the base times the height by 3. So the same will work for cones. The only difference is that the area of the base is found with pi r squared. Now using these methods, we can take the volume of various shapes. All you need to know is base times height. But what about a sphere? Let's use the same idea we use with the circle. Now let's look at the equation of volume of a sphere. We know that it's 4 pi r cubed divided by 3. But let's take this equation apart. It's really 2/3 times the diameter times the area of the circle. And I'll show you why with a fruit. So looking at it in one dimension, here's our circle, which we divided up into multiple pieces. And now I'm going to physically divide it into multiple pieces to get it to look just like our circle did in one dimension, but it'll look a little different in the third dimension. As you can see, this right here looks kind of like the pie piece that we had in our circle. Now looking at it in the third dimension, there's the diameter because it just went all the way through the fruit, but on the other side there's a curve. Now I'm going to stack them all up just like we did when we did the circle. Now here's our square, which gets our pi r squared. And our third dimension right here is the length of our diameter, but that doesn't account for the curves. So the pi r squared is made by the one dimension area, the diameter is the length, and we multiply by 2/3 because multiplying by just diameter and area is too much. So back to circles. So I made an x and y axis and labeled point A and B, and I'm drawing a half circle from A to B. So now what I'm going to do is I'm going to divide up the x-axis into equal lengths. Now I'm going to use these equal lengths as the width of rectangles. For the height of each of these individual rectangles, I'm going to use the height on the left side. So take the left side of any rectangle, go up, find what the point is on the half circle, and make that the height. So add up these areas and you get the area of the half circle. Underestimates on the left, but overestimates and makes up for it on the right. So multiply those areas by 2 and you get the area of the full circle. But that's just an estimate. If we want to get more accurate, we make more rectangles, or we just make the width of all of our rectangles really thin. To do that, we're going to do an instantaneous or infinite sum using the Roman s instead of the Greek s, which we use the Greek s in algebra. The f of x is our half circle. That's what it means. And the dx just means that we're making the width of all of these rectangles really small, because we're making it infinitely small. So adding up the areas of these new really thin rectangles from A to B will give us the actual area of this half circle. In lower maths we use delta x to mean change in x, but when it's infinitely small we use dx. So the area of this circle is going to be 2 times all of this right here. Now back to spheres. We can safely say that a coin is a circle because its width right here is very thin. So now what happens when we rotate a circle? It turns into a sphere. So now we're going to do the same thing with our circle here to find the volume of a sphere. We're going to rotate our half circle around the x-axis and it'll make our sphere. So what this is doing in terms of our rectangles here is it's turning them into little discs, which discs are cylinders. Way to learn how to take the volume of a cylinder. So really we're just adding up the volume of each of these little tiny cylinders, and we're getting the actual volume of a sphere. So to sum it up, from A to B, if we take the infinite sum of all of these cylinders whose height are becoming very small, it will give us the actual volume of the sphere. Pi r squared is the only thing changing for each of these cylinders. Each r value is found by the function. Now using these methods, we can take the area and the volume of many different shapes.